Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Reaching for the sky, the dream of the space elevator. For decades, the concept of a space elevator has captured the imagination of scientists, engineers, and science fiction enthusiasts alike. This visionary idea involves constructing a massive structure that reaches from Earth's surface into space, allowing for the transport of people and materials without the need for traditional rocket launches. The allure of a space elevator lies in its potential to revolutionize space travel by significantly reducing the cost and energy requirements of reaching orbit. This narrative explores the history, theoretical foundations, technical challenges, and potential impact of a space elevator, shedding light on one of humanity's most ambitious engineering dreams. The idea of a space elevator can be traced back to the early 20th century, when Russian scientist Konstantin Tsiolkovsky first envisioned a tower reaching into space. Inspired by the Eiffel Tower in Paris, Tsiolkovsky proposed a structure that would extend beyond Earth's atmosphere, anchored to the ground and held in place by centrifugal forces. While Tsiolkovsky's idea was purely theoretical, it laid the groundwork for future explorations of the concept. The modern notion of a space elevator was popularized by science fiction author Arthur C. Clarke in his 1979 novel The Fountains of Paradise. Clarke's portrayal of a space elevator captured the public's imagination and spurred interest in the scientific and engineering communities. He envisioned a giant cable stretching from the equator to geostationary orbit, with vehicles, known as climbers, traveling up and down the cable to transport cargo and passengers. The fundamental principle behind a space elevator is relatively simple. A cable anchored to the Earth's surface extends upward to a counterweight beyond geostationary orbit, approximately 35,786 kilometers, 22,236 miles, above the equator. The counterweight provides the necessary tension to keep the cable taut. As the Earth rotates, the centrifugal force acting on the cable counterbalances the gravitational force pulling it downward, effectively holding the structure in place. One of the key challenges in building a space elevator is the material required for the cable. The cable must be incredibly strong and lightweight to support its own weight and the additional loads imposed by climbers. Traditional materials, such as steel or aluminum, are far too heavy and weak for this purpose. However, advances in materials science have brought the dream of a space elevator closer to reality. Carbon nanotubes and graphene, both forms of carbon with remarkable strength-to-weight ratios, have emerged as promising candidates for the construction of the space elevator cable. Carbon nanotubes, discovered in the 1990s, are cylindrical structures made of carbon atoms arranged in a hexagonal lattice. They possess extraordinary tensile strength and low density, making them ideal for the space elevator cable. Similarly, graphene, a single layer of carbon atoms arranged in a two-dimensional lattice, exhibits exceptional strength and conductivity. While both materials are still in the experimental stage, researchers are optimistic about their potential to revolutionize space elevator construction. Assuming the development of a suitable cable material, the next challenge is the construction and deployment of the space elevator. The process begins with the launch of the cable from Earth to geostationary orbit. Once in orbit, the cable is gradually extended downward to the Earth's surface while simultaneously extending upward to the counterweight. This delicate operation requires precise control and coordination to ensure the cable remains stable and taut. Once the cable is in place, climbers equipped with electric or magnetic propulsion systems would travel up and down the cable, transporting cargo and passengers. These climbers would draw power from solar panels or wireless energy transmission systems, eliminating the need for traditional rocket fuel. The journey from the Earth's surface to geostationary orbit would take several days, but the cost savings and environmental benefits would be substantial. The potential benefits of a space elevator are immense. By eliminating the need for conventional rocket launches, the cost of reaching space would be dramatically reduced. Currently, launching a payload into orbit costs thousands of dollars per kilogram. With a space elevator, this cost could be reduced to a few $100s per kilogram, making space more accessible for scientific research, commercial ventures, and even tourism. In addition to cost savings, a space elevator would also reduce the environmental impact of space travel. Traditional rockets produce large amounts of greenhouse gases and other pollutants, contributing to climate change and air pollution. A space elevator, powered by renewable energy sources, would offer a cleaner and more sustainable means of reaching space. Furthermore, the reusable nature of the space elevator infrastructure would minimize waste and resource consumption. The construction of a space elevator would also have profound implications for space exploration and colonization. With a reliable and cost-effective means of reaching orbit, humanity could establish permanent habitats in space, such as space stations and lunar or Martian colonies. These habitats could serve as research outposts, manufacturing facilities, and even tourist destinations. The space elevator would enable the transportation of large amounts of cargo, including construction materials, equipment, and supplies, facilitating the development of self-sustaining colonies. Despite its potential, the space elevator concept faces significant technical and logistical challenges. One of the primary concerns is the threat posed by space debris. The cable of a space elevator would be vulnerable to collisions with micrometeoroids and man-made debris orbiting the Earth. Even small particles traveling at high speeds could cause significant damage to the cable, jeopardizing the entire structure. Mitigating this risk would require the development of advanced tracking and collision avoidance systems, as well as robust cable repair and maintenance protocols. Another challenge is the stability and control of the space elevator. The cable would be subjected to various forces, including gravitational and centrifugal forces, atmospheric drag, and tidal effects. Ensuring the cable remains taut and stable under these conditions would require sophisticated control systems and real-time monitoring. Additionally, the climbers traveling up and down the cable would need to be carefully coordinated to prevent oscillations and vibrations that could destabilize the structure. Political and legal considerations also play a crucial role in the realization of a space elevator. The construction and operation of a space elevator would require international cooperation and regulatory frameworks. Issues such as territorial rights, liability for accidents, and the sharing of costs and benefits would need to be addressed. the establishment of international treaties and agreements would be essential to ensure the peaceful and equitable use of space elevator technology. Despite these challenges, several organizations and research groups are actively pursuing the development of space elevator technology. The International Space Elevator Consortium, ISEC, and the Japan Space Elevator Association, JSEA, are among the leading organizations dedicated to advancing the concept. These groups conduct research, organize conferences, and collaborate with scientists and engineers worldwide to overcome the technical and logistical hurdles. In recent years, there have been significant milestones in the field of space elevator research. In 2009, the Japanese construction company Obayashi Corporation announced its intention to build a space elevator by 2050. The company envisions a 96,000-kilometer, 60,000-mile cable anchored to a floating platform in the Pacific Ocean, with climbers transporting passengers and cargo to a space station in geostationary orbit. While ambitious, this announcement underscores the growing interest and investment in space elevator technology. Another notable development is the Space Elevator Challenge, an annual competition organized by the Spaceward Foundation. The challenge aims to encourage innovation in space elevator technology by offering cash prizes for advancements in climber design, power transmission, and cable materials. The competition has spurred significant progress, with teams from around the world developing and testing prototypes of climbers and power systems. As we look to the future, the realization of a space elevator remains an ambitious but achievable goal. Advances in materials science, robotics, and renewable energy are steadily bringing the concept closer to reality. The potential benefits, from reducing the cost and environmental impact of space travel to enabling the colonization of space, make the pursuit of a space elevator a worthwhile endeavor. The narrative of the space elevator is one of vision, innovation, and perseverance. It is a story of humanity's relentless quest to push the boundaries of what is possible and to reach for the stars. The journey to build a space elevator will undoubtedly be challenging, but the rewards are immeasurable. As we stand on the cusp of a new era in space exploration, the dream of a space elevator serves as a powerful reminder of our capacity to imagine, create, and achieve.